We are given the graph of the first derivative of a function, otherwise known as f prime, and we're going to use this graph to make some conclusions about the parent graph, f. So I think one of the most important things to remember is, at a given x value on f, the slope of f is going to manifest on the y value of the f prime graph. We have to remember that the derivative tells us what the slope is at any given point on a function. So if we're at this point on f, that slope, whatever it is going to appear as the y value on f prime. Okay, keeping that in mind, I think it makes this process a little bit easier. So these are the items that we're going to look at on the f graph. So let's start with the first one. Where is f, the parent graph, increasing or decreasing? So if you think about any function that is decreasing, okay? Any function that is decreasing on an interval. So let's look at that f that's decreasing on an interval. What is true about the slope on a decreasing portion of f? It's negative. So if the slope of f is negative and the slope of f manifests in the y value on f prime, then we know anywhere the graph of f is decreasing, you have to have a negative slope, which means a negative y value for f prime. That means that it is going to be from x equals -3 to x equals -1, where f prime is negative. That is going to be where f is decreasing. Similarly, it's going to be in this zone here, where x equals 4 all the way to positive infinity. To review, the parent function is going to be decreasing when its slope is negative. The negative slope is going to manifest in a negative y value on f prime. And recall, a negative y value on any graph means it's located below the x-axis. Okay, conversely, we're going to look at where f is increasing. If f is increasing, then by definition, its slope has got to be positive. If the slope on f is positive, if f is increasing, its slope is positive, that's going to manifest on a y value on f prime that is positive. So where is f prime positive? Where are its y values positive? It's going to be from negative infinity to x equals -3. It's going to be from x equals -1 to x equals 4. These are all positive values of f prime. They're all above the x-axis. Folks, a moment ago I made the point that the slope on the parent function f becomes the y value on the f prime graph. Let me show you a neat trick. If we are asked to find where is the graph of f increasing, I want you to rewrite this in terms of slope. I want you to get the word slope involved to describe what we want to find. Well, if a graph is increasing, then we know that that means the slope is positive. Okay, so now we have this rewritten in terms of slope. Now, when we move from the f to the f prime, literally, we take out the word slope and we replace it with the words the y value. Take out slope and replace it with the y value. And that simple maneuver tells us that when the graph is decreasing, the y value is positive. Next, we're going to look at the relative extrema on f. Now, recall, on any graph of f, when you have a local or relative minimum, the graph is going to look like something like that. Now, what do you notice at that relative minimum? F is decreasing, then f is increasing. If f is decreasing, that means f prime must be negative. If f is increasing, that means f prime is positive. So to find a relative minimum on f, we're going to look for any places where f prime changes from a negative y value to a positive y value. Here, f prime is a negative y value. Here, f prime is a positive y value. That means that is a relative minimum. Remember, the slope of f manifests in the y value on f prime. To get a relative minimum, we want a position on f where the slope changes from decreasing to increasing. The slope changes from negative to positive. That means we need a point on f prime where the y value changes from negative to positive. So -1 is going to be a relative minimum. Okay, now let's look to relative maximums. On any graph of f, if you're looking at a relative maximum, let's see what's happening. You have a graph coming up and then coming down. You have a graph increasing. Okay, this is for a relative max. You have a graph that's f graph that's increasing and an f graph that is decreasing. You have an f graph that has a positive slope changing to an f graph that has a negative slope. That means on f prime, we're looking for a y value that changes from a positive to a negative. Where does that happen? It changes here from positive to negative, and it changes here from positive to negative. That means that -3 and +4 are relative maximums on the f graph. Now, take a note of one other thing, folks. Remembering that the slope of the f graph manifests in the y value on the derivative graph. Here, at that x value, what is the slope on the f graph? It is 0. That is why a relative maximum is going to have a slope of 0, and a relative minimum is going to have a slope of 0. That's going to manifest in an f prime value, y value of 0. Now, folks, before we leave the topic of a relative extrema on f using the graph of f prime, okay, we mentioned that a relative extrema on f is going to have a slope of 0, and that's going to manifest in a y value of 0 on f prime. And that's going to be true whether it's a relative maximum or a relative minimum. Now, I want you to be very careful. Not all zeros on an f prime graph, not all values of y equals 0 on an f prime graph is going to manifest on a relative or local minima or maximum on the f graph. And here's why. Let me give you an example. Suppose you had this on your f graph. One of these portions of the graph where indeed the slope is 0. Okay, let's look at what would happen here. Folks, the graph of f is decreasing up to that point, and it continues to decrease. That means if the graph of f is decreasing, the slope of f is negative. Then the graph crosses the point and it continues to be negative, that means this f graph is going to continue to have a negative slope. The slope of the f is going to manifest on the y value of f prime. So how could you have a scenario where the y value on f prime is negative, then the y value becomes 0, and then the y value becomes negative on the f prime graph? Well, here it is. If you have a graph that bounces rather than goes through on the f prime graph, that'll fit this scenario. Look, f prime is negative. If the y value of f prime is negative, that means the slope on f is negative. The slope is decreasing. Here the slope hits 0. The slope on the f graph is the y value on the f prime graph, both 0. Now the slope on the f graph continues to be negative because f continues to decrease. If the slope is negative on the f, the y value on f prime will be negative. So watch out for any f prime graph where you have a bounce as opposed to a through, like the ones in this particular example with the graph of f prime in black. In summary, in order for f to have a relative extrema, it has to go from increasing to decreasing or from decreasing to increasing. That means there has to be a sign change in f prime. You can't just look at the zeros and say all of the zeros are going to be indicative of a relative extrema. In these two cases where we bounce, there is no sign change. The f prime stays positive here. F prime goes to 0, but it stays positive. So this pink scenario on f would look something like this. A rising f, then a flattening with a slope of 0, but continuing to rise. That slope stays positive the entire time. No sign change in f prime. Here, there's a sign change. Here, there's a sign change from positive to negative. Again, negative to positive, positive to negative. That is what makes positive 4, negative 1, and negative 3 relative on extrema on f. Let's now look at the concept of a relative maximum on the parent f graph and how that shows up on the f prime graph using the switch maneuver. Folks, remember, a relative maximum on the f graph is where the graph increases and decreases. I want you to rewrite this in terms of the word slope. That on the graph of f is the same thing as saying that the slope changes from positive to negative. Now that we got the word slope here, we could take the word slope out, take this phrase, move it to the f prime graph, and replace it with the words the y value. The y value changes from positive to negative. So right here, positive to negative y value, that's going to be a relative maximum. Positive to negative y value, that's going to be a relative maximum on f. Let's now use the switch maneuver, investigating a relative minimum on the f graph. Recall, if we have a relative minimum, it means the graph, the y value of the graph is decreasing, and then the y value is increasing. How do we rewrite this in terms of the word slope? Well, the slope changes from negative when the graph is decreasing to positive when the graph is increasing. Folks, we move this same exact sentence, this same exact phrase over to the f prime side. We take out the word slope and we replace it with the y value. So if we have a relative minimum on f, it means the y value of f prime is going to change from negative to positive, and that's going to happen right here. It's going to change from negative to positive. Therefore, that will be a relative minimum on the f graph. Now let's move on to the concavity of f. Okay, this is an f graph that I just made up. It is not the one that pertains to this f prime graph. I want you to notice something, folks. Look at where the graph is concave down. And I want you to focus on the slope of this graph, not the y values. I understand that the y values on f are first increasing and then decreasing. That's not what I want you to focus on. I want you to focus on the slope of this white segment of f. Let's look at the slope. The slope here, I'm going to say, we're going to just call that positive 10. It's positive and it's pretty steep. Then in this area here, it's at 0. Then the slope turns negative. So the slope is right here. Let's call that negative 10. So when the graph of f is concave down, what happens to the slope? It starts at positive 10, it goes to 0, and then it goes to negative 10. In summary, the slope of the graph of f in any concave down interval is decreasing. If the slope of the graph of f is decreasing, what's happening to the y value on f prime? It is decreasing. So any concave down portion of a graph is going to correspond with a decreasing portion of f prime. So that would mean in this particular graph, we have decreasing f prime from negative infinity to negative 2, and we have decreasing f prime from positive 2 to x equals positive infinity. Any decreasing portion on f prime, anywhere the y value on f prime is decreasing, is going to be indicative of the slope decreasing on f. Where does a slope decrease as you move left to right? None other than a concave down portion of f. Again, I'm not interested in the y value of f. I understand that the y value of f goes up and comes down, but look at the slope. The slope goes from positive 10 to 0 to negative 10. The slope is decreasing on any concave down portion of the graph. Now, continuing our discussion on the concavity of f, we want to find anywhere on f where it's concave up. Look at this graph of f. Again, it's not necessarily our graph, but any graph of f that is concave up, I want you to focus on the slope. Again, not the y value. I understand the y value is going to decrease then increase, but watch the slope. The slope here starts out at about a negative 10. Then it goes to 0. Then it goes to positive 10. Okay, here we go. Starts at negative 10. Then it moves to 0. Then it moves to positive 10. The slope on a concave up portion of the graph is increasing. When the slope is increasing on the f, it means the y value is increasing on f prime. So anywhere f prime is increasing, which would in this graph would be between negative 2 and positive 2, that's going to manifest in a concave up portion on f. Look, from here to here, what's happening to the y values on f prime? They are increasing. If the y values on f prime are increasing, that means the slope on the f graph is increasing. When does the slope increase on a graph of f? None other than a concave up portion. That is the key. So anytime you think about concavity, I want you to think about f prime decreasing or increasing. If f prime is decreasing, if the y value of f prime is decreasing, that means the slope on f is decreasing. The slope of f decreases on concave down graphs. Conversely, whenever f prime is increasing, whenever the y value on f prime is increasing, that means the slope on f is increasing. Increasing slopes mean a concave up portion of the graph. Not interested in where f is decreasing or increasing. I'm just interested in when the slope and the slope alone is increasing. That'll manifest in a concave up portion of f. Finally, let's move on to points of inflection on f. Very clearly, a point of inflection on f is when there's a change in concavity. So we're going to go to f prime and we're going to see where f prime changes from decreasing, meaning f prime y value is decreasing, manifests in a decreasing slope. A concave down portion on f changes to an increasing portion of f, where the y values are increasing, means the slope is increasing on f, means it's concave up. So anywhere f prime changes from decreasing to increasing or increasing to decreasing, you will see a point of inflection. So there will be a point of inflection on f at x equals -2, where there's a change from decrease to increase, and also x equals +2, where f prime changes from increase to decrease. Now, one thing I want you to notice, folks. Look at the slope of f prime at the points of inflection. It is 0. Remember, the slope of f prime is going to manifest in the y value on f double prime. And remember how we find points of inflection when we're given the function itself, no graph. What we do is we set f double prime equal to 0, and then we investigate on both sides of that critical point. Or we set it to f double prime equal to undefined. But at that critical point that we're going to evaluate either side of to determine is if f prime double prime is negative or positive, meaning concave down, concave up respectively, at the critical point, at the potential point of inflection, f double prime equals 0. The slope of f prime is going to manifest in the y value of f double prime. That's why it makes sense that any relative minimum or maximum on f prime, which has a 0 slope, is going to have an f double prime equal to 0, which makes it a potential point of inflection. Find where f is concave up using the switch maneuver. Folks, we're going to rewrite this concept in terms of the word slope. So a concave up portion of the graph, what's true about the slope? The answer? The slope is increasing. So as soon as you hear the words concave up, I want you to change it to where is the slope increasing. Recall, it goes from -10 to 0 to +10. We're going to take this phrase, we're going to move it over here to this graph. We're going to take out the word slope and we're going to replace it with the y value of f prime. So in order to go from where is f concave up, we have to go where the y value of f prime is increasing. We take out the word slope and replace it with the y value of f prime. So where is the y value increasing on f prime? From x equals -2 to x equals +2. Next, we're asked to find where the f graph is concave down. How do we rewrite this concept using the word slope? How do we get slope into this concept? Well, what is true about any concave interval on a graph? The slope is decreasing. Recall, in a concave down portion of the graph, it's going to be going from positive 10 to 0 to negative 10. Positive 10 to 0 to negative 10. That's a decreasing slope. Decreasing slope, concave down. We're going to take this phrase and we're going to replace the word slope. See if I can grab it. We're going to replace the word slope with the words the y value of f prime right there. So where is the f concave down? It's where the y value of f prime is decreasing. Here is going to have a concave down f, and here it's going to be a concave down original function f.